Welcome to my YouTube channel PCM Academy. We have discussed in the last class about the second postulates. Actually, we are in quantum mechanics and we have discussed a lot of things about quantum mechanics, but now we are discussing the postulates of quantum mechanics. Okay, so we will discuss today postulates 3 basically, and in the last class we have discussed postulates 1 and postulates 2. There are 5 postulates of quantum mechanics and they are the backbone of quantum mechanics, you can say. So before going to analysis the postulate 3, let me tell you about an important topics that is max Born interpretation. This is basically a probabilistic interpretation. Okay, so what this interpretation say, that if you know that we have a wave function psi of t or the k vector psi of t that represent a state of quantum system, but the psi of t has no physical significance. You can be surprised that this psi of t that we have represented in this way, so it have no physical significance. But if you talk about mod psi square, or you can say psi x comma t, so let me write in this way, that will be more better. Psi will depend on both x and t. So if you talk about psi x and t, this is no physical significance. But if you talk about mod psi square, then this is the probability density at time t. Okay, so this is actually the probability density of finding the particle at time t. Okay, so what is the probability that if you talk about mod psi xt square dx, then this is the probability of finding the particle between x and x plus dx at time t. So this is the probability of finding the particle. This is probability of finding the particle between x and x plus dx at time t. Okay, at time t. But if you talk about in 3 dimension, that is psi r comma t mod square d tau, then this is the probability of finding the particle at r within the volume element d tau. Okay, but if you talk about psi x y z in component form, instead of r you can write in psi x y z t mod square. In that case d tau can be written as dx dy dz. So this is also the probability of finding the particle between x to x plus dx and y to y plus dy and z to z plus dz, in this limit. Okay, at time t. So you can write in this 3 way of probability of finding the particle within a particular region. Okay, so what will be the total probability? You can see this is just in a small region, but if you talk about the total probability, that will be integration of this. So you can write that throughout the whole space. So integration throughout the whole space, that is minus infinity to plus infinity, you can say x y z all run from minus infinity to plus infinity, and if you integrate this x y z and t mod square dx dy dz, so that will be obviously 1. You know that the total probability will obviously be 1. And if the wave function follow this property, then this wave function psi r comma t, or you can say x y z comma t, is known as the normalized wave function. Okay, is known as the normalized wave function. So you should remember this thing. This max Born interpretation is also very important when you talk about the probability of finding the particle between any interval. Okay, so this is how you can remember this. Now the next thing that I am going to start is nothing but the postulates 3. So third postulates of quantum mechanics. Okay, so this is the postulates 3. So we have discussed 1 and 2 previously. So now we will discuss about the postulates 3. Okay, now what we are going to tell about the quantum system in postulate 3 is So in first and second postulates, you can see in the first postulate what we have said, that how we can define a state of the system, and in the second postulate we have told that how a physical measurable quantity can be written in terms of operator. Now here we will tell that if you measure a observable or a physical quantity on a certain state, then what will be the state after measurement? Okay, so the state will be changed whenever you measure on a state psi. Whenever you measure some physical quantity on the state psi, then obviously after immediate measurement the state vector psi will be changed, and what will be the psi after? That will be the main statement of the postulate 3. So suppose we have an operator, or you can say a physical observable A, and corresponding to this observable A, obviously there is an operator A cap. Now suppose we have measured A cap on psi of t, and we will get some value that will be an. Suppose that will be an. This is the eigenvalue. This is the an is the eigenvalue of the state psi n. Okay, so whenever you have a observable or a operator, then corresponding to that operator there are several eigenvalues, several eigenvector, and corresponding to each eigenvector there will also be eigenvalue. Suppose we have this A cap is suppose, and obviously we have told earlier that this A cap should be Hermitian operator. Okay, so suppose we have, so A cap, suppose A cap is just Hermitian operator, and corresponding to this operator there are some eigenvector, that is suppose psi 1, psi 2 and psi 3 dot psi n. Okay, and for each of the state, if you operate A cap on psi 1, then you will get eigenvalue A1. If you operate A on psi 2, then you will get eigenvalue A2, similarly A3 and an. Suppose in general when you operate on psi, and this psi actually the linear combination of this. Okay, if A cap is the Hermitian operator, then obviously it will form a complete basis that I have told in the second postulates. Okay, so obviously we can write psi of t as the linear combination of this, that is C1 psi 1, plus C2 psi 2 plus C3 psi 3 plus dot Cn up to Cn. Let me write it as Cn. Okay, so it will be just Cn psi n. So this is how we can write psi of t. Now if you measure any of the eigenvalue, suppose psi n, corresponding to the eigenvector psi n, if you measure an corresponding to the eigenvector psi n, suppose, then what will be the eigenvector after immediate measurement of an? So that will be the basic statement of postulates 3, and that will be psi after. So that will be psi after, and this is nothing but psi n and psi n with psi of t, or you can say psi of t with psi n, with psi n, or you can write in this way as right. Okay, psi n psi of t. Okay, so this will be the main statement. Now we will prove this. Okay, this will be the main statement. So this is the statement of postulates 3. Actually, this is the statement of postulates 3. That what will be the wave function after measurement of the eigenvalue of that state. Okay, so this is the psi after, and that is psi n, and this is psi n psi t. This is actually the projection of psi n on psi t. Okay, so we can prove this result very easily, because we have this equation. If you take this as equation number 1, and again the eigenvalue equation you can take, so you can take the eigenvalue equation also, that is A cap psi n on the state psi n, that will be just an psi n. Okay, now if you want to measure A cap on psi of t. Okay, so let me operate this equation 1 on a k by a cap. So what will be the psi after? So if you operate on psi of t, then you will get just a1, sorry, c1. So it will be just c1 a cap psi 1 plus c2 a cap psi 2 plus dot dot plus cn a cap psi n. Okay, and let me write in this way. Okay, so this is the a cap actually. Okay, now you know, if we want to measure, if you want to measure the state psi n only, then obviously the measurement of psi 1 and psi 2 will be 0. So you will get only one measurement at a time. Okay, because this psi of t will be at any state. It may be either at psi 1 or psi 2 or psi n, but psi of t can be written in the linear combination of all this eigenvalue, all this eigenvector, but at a particular time you will get only one of the eigenvalue. So if you get the eigenvalue an, that is a cap psi n on I, that is an, then you will get other result, obviously 0. So this will be 0 plus 0 plus this will be actually cn an psi n. So actually this is the psi after. So cn an is the psi after. You can, if you compare both sides, so you can see this is a cap psi of t is equal to just this is an and cn psi n, cn psi n. Okay, so it can be written in this way also, where this is the eigenvalue an, so it can be write a cap cn psi n. You can see, you can write it in this way. So a cap psi n actually an, so we can write a cap psi n cn psi n, so that is an. Okay, so you can compare both sides. So you can see that after measurement, after operate a cap on psi t, so psi t will become cn psi n. So this cn psi n is actually the psi after. So what will be the psi after? If you talk, then psi after is nothing but cn psi n, cn psi n. Okay, so we have to find out cn. Now how you can find out cn? Cn is actually, if you see, cn is actually this psi n psi t. So if you take the dot product of psi n and psi t, then what will happen? So this is suppose our equation number 1. Now we have to find out cn. So how we can find out cn? So we have psi of t actually, that is the linear combination of psi 1 psi 2, that is c1 psi 1 plus c2 psi 2 plus c3 psi 3. So let me write directly cn psi n plus cn psi n. Now if you take the dot product of psi n with psi of t, so psi n with psi of t, so what will happen? Psi n with psi of t, yes, psi n with psi of t, then what will happen? So it will be c1 psi n psi 1, the dot product, plus c2 psi n psi 2 plus dot dot cn psi n psi n. Okay, the dot dot plus you will get cn psi n with psi n. Okay, you will get this. Now you know, as psi 1 psi 2 psi 3 are the orthonormal wave function, so our orthonormal condition was psi I psi j, that I have discussed earlier also, and that is equal to delta ij. That means it will be 1 if I is equal to j, and it will be 0 if I not equal to j. So we have discussed this earlier. Okay, so you can see here that this psi n psi 1 is also 0, psi n psi 2 is also 0, but this psi n will be 1 because here I is equal to j. So now what will happen? This psi n with psi t, that is the dot product, that will be just cn. So you can see this is just cn. So this Cn in equation number 1 can be substituted by this. So what will be psi after that was nothing but Cn sin, and this Cn can be written as sin psi t. So sin I can write earlier, then we can write this is number, you can write wherever you want, okay. So ft. So this is our statement of postulate 3.